So yeah, I'm going to be talking a bit more on the academic side this time. So I'll just give you a very brief overview of what a fusion reactor could look like, and I'll show you a 1D schematic on the right. So the fusion reactor consists of many components. The plasma is really the thing that actually creates the energy, and they come out in neutrons, radiation, etc. We have heating and current drive systems, such as the radio frequency heating that was mentioned in previous talks, and those are used to heat the plasma to thermonuclear temperatures, and the current drive is used to sustain plasmas for long periods of time. Now, because this is supposed to be an energy reactor, there's going to be a lot of heat coming out, and the first wall is necessary to handle the heat flux and to handle plasma material interactions as well. This leads you further along into the blanket. The blanket has multiple functions. I'll mention two today. One is to breed tritium. Tritium is an isotope of hydrogen and it is not naturally available on Earth, so we need to breed it. The second one is that we need to convert the energies that you get from neutrons into thermal energy in some form of thermal cycle, and that's what the blankets are usually used for. Now, in the next step, we have a shield, and that's a neutron shielding. Neutrons do pose some safety hazard, as well as tritium as well. And then lastly, all this needs to be confined in vacuum. The vacuum vessel not only provides the lower pressure you need, it provides a mechanical barrier so that a lot of things cannot escape. And then lastly, the focus of the last talk was on the magnets, and those are necessary for external magnetic field that is necessary to create the plasma. So the very last one I mentioned is diagnostics, which cross-cut all these components and is the subject of today's talk. So diagnostics in a fusion reactor will mostly be needed for monitoring and safety control. So in sort of order of priority, the first one will be personnel safety. So as I mentioned to you earlier, tritium is radioactive. 14 MeV neutrons do pose a safety hazard to humans. So you need one diagnostics to monitor that. Machine protection. So the magnets have pretty high power. Heating and current drive systems have high power. You don't want the heat to go to various places. You don't want some other things to go to places that you do not want to. So that's machine protection. Then lastly, machine control. So the plasma by itself often can have transients, and you need certain techniques to control the plasma. And to do so, you need to monitor the plasma and use that to inform your control decision making. So diagnostics can be used to reliably measure signals. They usually come out of some sort of digitizer or some sort of electronics of some sort. Diagnostic models are really needed to convert these signals to something meaningful and physical, so that you can understand the safety implications, the protection and control implications. So in today's work, besides the monitoring safety, diagnostic models are used to better understand various fusion components. That's what the academic side. The goal and hope of that is, of course, with better understanding, you can better design a fusion reactor and extrapolate or feed into models that can help you design a fusion reactor. Okay, so that brings me to today's talk. And really, the goals of the rest of the talk is to provide some snapshots of how COMSOL could be used to understand measurements made by diagnostics. I showed three examples here: radio frequency fields in plasma using visible spectrometer diagnostic, measuring heat flux on first walls using infrared cameras, and measuring flow velocities in liquid metal loops using an eddy current flow meter. So these examples were mostly chosen due to my own experience. I also wanted to show a wide range of different physics, and it's a wide range of different components that are necessary in a fusion reactor. So let me start with the radio frequency fields that we use for heating and current drive. So it turns out there is an effect known as the dynamic stock effect spectroscopy, and that can be used to measure the magnitude and direction of radio frequency fields. And it does this by actually probing the quantum mechanics of atoms that can be decided by the Schrodinger's equations. So if you recall your quantum mechanics, this is what it looks like. There's an additional term here for the steady state magnetic field as known as the Zeeman effect. And then the dynamic stock effect is the time-dependent term for the electric fields. A simulation of that is shown on the top right for various angles. You can see that in different colors, which present different angles, you can see that the shape and the curves are very different. And this is done what is known as the D-beta spectrum. So this measures the intensity as a function of visible wavelength. So this type of a spectral shape profile can be measured using what is known as a visible spectrometer. A cartoon of that is shown on the right here. And we show a spectrometer here that views a line of sight signal that's in front of a radio frequency antenna that's actually output CMOD, which was discussed in the previous slide. So what we use console here, and what has also was actually done with some of the work that was referenced in the previous talk by Shinichi, was that we, based on that work, we have used a cold plasma model to solve for the radio frequency fields. This is done in 2 dimensions here, solving the Helmholtz equation in 2D axisymmetry. And this is done using Console's RF model. I'm going to be brief here, but the dielectric tensor is a 3x3 asymmetric tensor. It depends on the magnetic fields, the densities, and the density fluctuations. If you know what the antenna spectrum is, you can actually do a 3D calculation by summing over many toroidal mode numbers, and that's described by this equation right here. And on the plot on the top right is an example of what you can get in 3D image of what the radio frequency fields look like in these simulations. The bottom figure shows you what the spectrometer sees. So you can see that this is now a cone. If you look very carefully, almost all the signal happens in front of the radio frequency antenna. And by using a model such like this, it just allows us to localize the spectrometer signal. Now, one thing that actually proved troubling to us was that the measurement did not agree with the model. And you'll hear this theme a lot where we try to make the measurements and model agree today's talk. So I'll run through how we figure this out. So one of the key inputs is the density on the left. The middle is the magnitude of the RF electric field, which is one of the outputs. And the right is the magnitude of what we call the electric field angle. We zoom in on the blue square in the next few slides, because that's where the spectrometer is viewing the information. So I show you 5 separate simulations done for 5 different input density and density fluctuations, and those are shown at the top here. On the top left case is one without density fluctuations. You can see also cases with blobs with density fluctuations that are periodic of different wavelengths as well as different amplitudes. And so it turns out that the outputs can vary quite a bit depending on the inputs to your model. So on the bottom left is the very smooth looking electric field pattern. However, when you start adding fluctuations, you get strange scattering events. You get events where you seem to see cavity modes, and then you get backscattering events, or you can also get events where the fluctuations don't seem to affect the plasma very much. So this is telling you how important this input is to the model. So for the same 5 simulations I mentioned here, we can also plot images of what the angle looks like. So again, very similar qualitative conclusions can be met. On the bottom left, you can see that it's a very smooth figure in terms of angle. But if there's scattering, then the angle also changes. If there's these cavity modes or something, the angle also changes. Backscattering, the angle changes. If the fluctuations don't affect the plasma, then the angle does not change very much. So what we're seeing in real life? So this is where we combine the simulations with the measurements. So on the right here, we show you a simulation color plot where the x-axis is the density fluctuation amplitude, the y-axis is the fluctuation size, and the color represents the angle. If there are no fluctuations, or when n tilde over n equals 0, you can see that the simulation, will say something on the order of 70 to 80 degrees. It turned out that the spectroscopy measurement I mentioned before is actually closer to like 45 degrees, and the measurement and model will only match in this little operation space that I highlighted in the oval. So it turns out we didn't actually measure the fluctuations on these experiments, but on previous experiments that were admittedly somewhat different, the filament sizes as well as the density fluctuation amplitudes do actually lie in this range. So this gives us some confidence that the measurements and modeling matches. But for it to match, this means that there is turbulence in the plasma. The turbulence does affect the radio frequency heating, current drive, absorption and propagation. and this needs to be considered going forward. And if you want to read more details, please follow that paper below. Okay, so let me now move on to the second topic, which is measuring heat flux on first walls using IR cameras. So we have an IR camera that is installed on a linear plasma device that I show here. This plasma device is called a proto-MPES. It consists of a helicon source to produce the plasma, electron cyclotron heating to heat the plasma, to the IR camera that measures the surface temperature in front of the material target plate. That is shown on the bottom here. You can see that after the plasma, when we take out the target, it's very clean behind on the back of the plate, but on front of the plate, we see discolorations. So the IR camera directly measures the 2D surface temperature, but what we really want to get is the heat flux. And to do that, you again need to do modeling. So here we use COMSOL's heat transfer model to solve for the 3D heat equation. This is what is shown here. We mostly use material libraries to understand how the different material properties change with temperature. On the bottom left, I show you what the surface temperature inputs looks like for a example case. The key boundary condition is that the IR camera temperature is used as a boundary condition on the front plate. So this is quite a bit simpler model than the ones I showed you in the first topic. And on the right, you can sort of see an example of what the heat flux looks like. But again, going back to this point where, do the models and measurements make sense? One way you can do is try to compare to another measurement to see if they agree or not. So here I also show you measurements using a Langmuir probe, which measures the plasma density and temperature, and it can infer a heat flux using this formula below. And the tricky thing about this formula is the sheaf transmission coefficient, which can vary quite a bit. So I'll show you some experimental data on the right. So on the top right figure is the density as a function of the magnetic field near the electron cyclotron launcher. You can see it has quite a bit of variation depending on the parameters that you have input. In the middle is the measurement of the Langmuir probe for the temperature for the same cases. At the bottom, in the shaded colors, is what the inferred heat flux is from the Langmuir probes. On the same plot, in the solid lines, is what the IR camera it measures at the same location that the probe measures. And you can see that there's pretty good agreement in both the magnitude and trend for a wide range of cases. And this is only true if you assume a sheaf transmission coefficient between 5 and 7. That's what the shaded error bars represent. If you assume a value of 5, that's the minimum. If you assume a value of 7, that's the maximum that's shaded. So this turns out that at least for a simple sheaf energy theory, this is the expected theoretical range. So this gives us some confidence in both the measurement and the models. So if you have confidence in the measurement, that allows you to sort of gain more understanding of physics. I'll show you one example here, and if you want more details, you can view the paper again at the bottom, where we have measured the target heat flux as a function of the helicon magnetic field on the y-axis and the helicon power on the x-axis. And our major goal here was to better understand how these helicon modes operate. As you can see, by changing these parameters experimentally, there is a wide range of different possibilities. From an ideal perspective, we would like to see a lot of heat flux, particularly at the center region. So this is best done here in the 90 kilowatts case for the power and the 47 millitesla case. However, at other powers and magnetic fields, you can get a lot of edge absorption, and we have identified that as what is known as triple P screw modes in the literature. But more or less, the IR camera has provided us some eyes in helping us improve operations and help us in terms of understanding. Clearly, more power seems to be giving more heat flux as a whole if you integrate over the area. Also, it's also clear that the magnetic field needs to be optimized. 47 millitesla seems to be doing better than 67 and 28 millitesla. Okay, so let me jump to the last topic, which is measuring flow velocities in liquid metal loops using an eddy current flow meter. So here, I would first discuss what the eddy current flow meter is. It's basically a very simple set of coils shown on the top right. If you apply an AC current on what is known as the primary coil, and then measure the difference in the secondary coils, if there is no flow through this sensor, then the voltage difference in the secondary coils is 0. If there is some flow, then the voltage difference between the secondary coils is proportional to the velocity. So we define this as a sensitivity here, which is the voltage difference of the secondary coils over the applied AC current on the primary coil. And what we wanted to do here was to test these sensors to get an idea of how it can measure flows and flow profiles, with the eventual goal of more relevant testing in reactor-relevant liquid metal loops. As mentioned earlier today, liquid metals is one of the leading concepts for blankets that we use in the fusion reactor. So on the bottom, we show you an example of what the measurement looks like in a loop. The flow goes in, it goes into one of our sensors, the flow wraps around, and then it goes through two more sensors before flowing out. So we have measurements at 3 different sensors at 3 different diameters. So again here, that was what the measurement setup is, but the measurement measures the sensitivity as a function of frequency. What we desire is a flow. So this is again something you need modeling to interpret. So here we use the combined Navier-Stokes and Ampere's law. So this is done using the console CFD module as well as the AC-DC module. We choose a 2D axisymmetric geometry here. For the Navier-Stokes, we assume that it's incompressible and turbulent. I would note that the Reynolds number is estimated to be greater than 20,000. The critical Reynolds number is about 2,300 to transition from laminar to turbulent in a circular pipe. So the right shows you an image of the geometry and the boundary conditions. So for the Navier-Stokes, this is a very standard inflow velocity boundary condition with the outflow pressure boundary condition. And on the walls of the liquid metals is the no-slip boundary condition. So once we have the flow, that serves as input into the Ampere's law, and it has additional Lorentz force so that we can capture the flow terms. And this is used to calculate the sensitivity that I mentioned on the previous slide. Okay, so let me just jump right into the comparison of the experiments and modeling. So again, as I mentioned to you earlier, you want to know if these things work before you can make any conclusions. So in the symbols and different colors, I show you the experimental data for the 3 sensors. On the lines, the color lines are the console simulation results. As you can see, this is the sensitivity as a function of frequency. The measurements and modeling agree quite well in both magnitude as well as trend for all these cases. And that, the normalized root mean square error is less than 10%. So I think this is quite good agreement. And I think this provides us confidence that we can do both the measurement and modeling can't be at least too far off. So this brings me towards what we can do with this. So one of the new things we've done with this sensor is that we're able to not only measure the mean flow, but we're able to measure a flow profile. The reason we do that is that at multiple frequencies, each frequency is sensitive to a somewhat different radial location due to what is known as the electromagnetic skin depth. So basically, from the launch current from the primary coil, there is somewhat of an exponential decay of the magnetic fields. At low frequency, that decay length is quite large, so it can penetrate all the way into the center of the liquid metal. As you increase the frequency, the skin depth decreases and it penetrates less and less. And at high frequency, the penetration is quite small. So by measuring at different frequencies, you might be able to get a different flow profile. So I outlined here a preliminary proof of principle example. The model has flow profiles input, the sensitivity and as a function of frequency is output. The measurement is exactly the opposite. So this is a very standard inverse problem. So one way to do this is shown in this algorithm here using the Ampere's law calculation only. You make some assumption on the flow profile. In this case, we assume it's the sum of n heaviside functions, and then you use console to run these simulations for each of these. So I'm not going to go into too much detail here, but if you do it, it results in a relatively linear algebra problem, and you can minimize the AV minus B here for various choices of V, where V is your flow and B is your sensitivity. If you do that, you can get results for the flow profile. So the solid line and symbols show you what the experiment measurements is using this algorithm. The long dashed lines is a simulation with turbulence. The short dashed lines is a simulation for laminar flow. You can see that the measurement agrees quite well with the modeling with turbulence, and that's somewhat expected based on the high Reynolds number. But however, when we go into more complicated flows, such as liquid metal blankets in the external magnetic field, I think this sensor could provide much more interesting information by measuring the flow profiles in that aspect, and we hope to do that sometime in the future. So I'll leave this, my last slide here as a summary since I'm running out of time. As I showed you 3 different example applications using a variety of different console models, the RF module, the AC/DC, the CFD module, as well as the heat transfer module. So thank you.